Okay, in this section we're going to talk about a particular very important type of group called cyclic groups. And they're called cyclic groups because in some sense they can be represented as a cycle. You remember we had cycles in permutation, so cyclic groups are very closely related to cycles. Okay, so let's do some examples. Consider the group Z. Let's try to find the smallest subgroup of Z that contains the number 1. Okay. Now this is Z with addition because we don't have Z star, right? Okay. So let's start with 1. All right. Now, if it contains 1, it must, since it's a group, since the subgroup must be closed under addition, then 1 plus 1 must also be in it. Well, here, let's go through the steps like this. If it's a group, then 0 must also be in it. So 0 must be in this set as well. All right. Furthermore, if it's going to be a group, then the inverse of 1 must be in. So minus 1 has to be in. All right. And then we have, since P is closed under addition, then 1 plus 1 must be in. So that gives us 2. Minus 1 plus minus 1 must be in, so that gives us minus 3. And I think that you can see that what's going to happen is that you're going to see that the smallest subgroup that contains 1 must be, in fact, all the integers. As soon as I know that the subgroup contains 1, I know it must contain all the integers. Okay, very interesting property. Okay. So in fact, this one element, this one single element 1, that determines the group uniquely. So we use this notation, that this group generated by this one element, this subgroup of Z generated by this one element, is denoted by angle brackets 1. Okay, so let's generalize this concept. Given a group and an element in the group, then the set generated by the element is denoted by angle brackets A and is defined as the set obtained by repeated operation on the identity E by the group elements A and A inverse. Okay, so what does that mean, repeated operation? So we take E, we can operate A on that, then you can operate A again, then A again, and that will give me A squared, A cubed. Same thing with A inverse. I can take A inverse, repeatedly operate A inverse, and I get A inverse, A minus 2, A minus 3, and so on. So we can write this in abbreviated form. Notice that these powers are all of the integers, so I can write A angle brackets in this abbreviated form like this. Okay. Now remember again that if you have an additive group, although these look like exponents, that would be A plus A plus A plus A, and so on. You're just repeating the group operation. An alternative designation for this angle brackets A is the orbit. Okay. Here's the comment about additive groups that I talked before. Okay, if you have a group where some element is actually, the orbit of that element is the entire group, then that group is called a cyclic group. Okay, so in fact the integers is a cyclic group generated by the element 1. Why? Because Z was equal to angle brackets 1. Okay. Now that doesn't mean that 1 is the only generator of Z. It turns out that minus 1 is also a generator. Okay, so you can find some other examples. Okay, and here's some other examples of that same concept. A group may have more than one generator, or a group may have no generators. Okay, all right. So we defined a cyclic group as a group that can be expressed as angle brackets A. All right. Now let's consider the elements of a group, and let's consider the angle brackets of A for arbitrary group elements. Now that may not give us the entire group, but I wonder, will it give us a group? Consider, for instance, if I take the integer 4 under the operation of addition, that generates this set. You can see that by repeated operation of 4, which happens to be the set 4Z. And in fact, 4Z is a subgroup of Z that was shown before. Okay. Now, since 4Z is generated by angle brackets 4, it's a cyclic subgroup. It's not all of Z, but it's a subgroup, and it's cyclic because it's generated by 4. Okay. Some more examples of cyclic subgroups. Okay. Okay. Now, it turns out that whenever you take the orbit of an element, you get a subgroup. It's always true. So this is a way of generating subgroups of a group. Take any element, take its orbit, in this way, a to the different power, the z powers, and that will get you a group. Furthermore, the angle brackets A is the smallest subgroup of G that contains A. Now remember, we found out that when you took 1 and angle brackets 1, and we found that the angle brackets 1 was equal to Z. And that was that if you have a subgroup of Z that contains 1, it must contain all of angle brackets 1. So there's no smaller subgroup that contains 1. So that's true in general, that the orbit of A is the smallest subgroup of G that contains A. Okay, and you can go through this definition. You're just going to show the subgroup properties. And to show it's the smallest one, you have to show that there's no subgroup that's smaller. Okay. All right. So here we have a definition: cyclic subgroup. The orbit of A is called the cyclic subgroup generated by A. All right. Now let's specialize to finite groups. We'll look at finite groups. Okay. So if G is a finite group, so let's consider a particular element, and we'll operate on itself again and again and again. I'm not taking the identity. I'm starting with A. Operate on itself again and again and again. All right. Now, G is finite. Now, this is a great principle here. Since G is finite, this can't go on forever. This sequence must end up repeating. There must be duplicate elements. I shouldn't say repeating. It must contain duplicate elements. Okay. So what does that mean? That means that 2 of the elements in the sequence must be equal. So there must be 2 powers k and l such that a to the k is equal to a to the l. All right, so what you want to show from this, that a to the k equals a to the l, you want to show that, in fact, there must be a power of a such that a to the m is the identity. All right, and it follows fairly directly from this fact that there must be 2 values k and l such that a to the k is a to the l. And these k and l, of course, have to be different. So using this fact, you can show that there must be some power of a that gives me the identity. So this is a great thing, that if I just take powers of a, eventually I have to end up with the identity. Now, once I end up with the identity, if I keep multiplying by a, I'm going to repeat the cycle. So here you kind of see this cycle going on. Okay, so you define the order of an element A as the smallest integer n such that a to the n is equal to the identity. Okay, and we write that using absolute value of a. So this is another use of the absolute value sign. Okay. Now, in the case of integers, we know that this doesn't happen, so we say that the order is infinite. Okay. Okay, so some more exercises. Exercise. Okay, and you should look at this example, that not every group is a cyclic group. Okay, you'll find out that every group has cyclic subgroups, but in this case, if you look at S3, you'll find that all the cyclic subgroups, none of them generates all of S3. Okay. Important fact, every cyclic group is abelian. All right. Basically, you can say it's because every element of a cyclic group is a power of A, and the powers of A must commute because they're just copies of A. So follow through this proof and see this important fact that every cyclic group is abelian. Okay, let's look at subgroups of cyclic groups. Okay. So what possible subgroups are there of a cyclic group? Turns out that every subgroup of a cyclic group is itself cyclic. Really? cool fact. Okay. The idea of this proof is that if you have a subgroup of a cyclic group, well, if you have a cyclic group, it must be something like A. Okay. If you have a subgroup of a cyclic group, you find the smallest power of A in my subgroup. Okay. And suppose that's A to the m. Then you can show that in fact H must be equal to the orbit of A to the m. So that's what's actually going to happen. That it's kind of like a greatest common multiple sort of thing, that if I find that if I have a cyclic group, I take a subgroup, look through that subgroup for the smallest power, and then that subgroup itself must be the cyclic group generated by that smallest power. Okay. All right. So here's the formal proof. And you'll see how this works out. Let G be a cyclic group generated by A. Suppose that H is a subgroup of G. If H is just equal to the identity, then H is cyclic, okay, because this subgroup is E is the subgroup generated by the identity. Okay. Now suppose that H contains some other element distinct from G, distinct from the identity, then G can be written as A to the n. We can assume that n is bigger than 0. Let m be the smallest natural number such that A to the m is in H. Okay. Okay, such an m must exist there because there must be a smallest m, because it can't be smaller than 0. Okay, we call this the principle of well ordering. Okay, but it's very intuitive. All right, so we claim that this smallest power of A is in fact a generator for the entire subgroup. First of all, we must show that every element of this subgroup can be written as a power of this A to the m, where m is the smallest power of A. Okay. Since H prime is in H and H is a subgroup, then H prime is equal to A to the k. Okay. Now if you divide H prime, well, I'm sorry, we don't do that. Let's go a little farther. Using the division algorithm, we can find numbers q and r such that k equals mq plus r. Remember what m is. M is the power that appears in this element H. K is the power that appears in this element H prime. Okay, so we're dividing the power of H prime by the power that appears in H. Okay. So when we get that, we'll get some kind of remainder, where the remainder is between 0 and m. So that means that A to the k equals A mq plus r. So we have this as A to the mq times A to the r is H to the q times AR. Okay. So in fact, I can obtain A to the r by multiplying both sides by the inverse of H to the q. I've just taken both sides of this equation and I've multiplied both sides by the inverse of H to the q. All right, this really should be the H to the minus q A to the k, but since the group is commutative, it really doesn't matter. Okay, I can do this in either order since the group is commutative. Okay, we've shown that cyclic groups are commutative. All right, so I can express A to the r as a product of group elements. So A to the r must also be in H. All right, however, m was the smallest positive number such that A to the m was in H. All right? Now, but here we found out that A to the r, that r must be between 0 and it must be less than m. All right? So since m is the smallest positive number, then r cannot be a positive number. It must be 0. Okay, so r must be 0, and that means that this other power must be equal to a multiple of my smallest power. Okay, very nice proof. Think about this. Take a couple times to go through this and understand this proof. Okay, similar proof here. Let G be a cyclic group of order n, and suppose that A is a generator for G. Then A to the k is equal to the identity if and only if n divides k. Okay. All right, remember the cyclic group of order n, then a to the k as e if and only if this power k is divisible by the order of the group. Okay, follow this proof. Suppose that a to the k is e. By the division algorithm, that means that k can be written as n times q plus r. Again, r is less than n. It's a non-negative number less than n. Okay. But then I can write e as a to the k is equals a to the nq plus r, so I can write it this way. But a to the nq is equal to the identity to the qth power. Remember, a to the nq is equal to the identity to the qth power. Identity to the qth power is identity, so I have a to the r. So that means a to the r. So what did I find out? That a to the r, where r is this remainder, must be the identity. However, m was the smallest positive number such that a to the m was e. Okay? So what does that mean? That means r cannot be a positive number since r is less than m. So we must have r is equal to 0. Sorry, this is a misprint here. This shouldn't be m. This should be n. That should be an n there. That should be an n there. Okay, so you can make that change in your book. Those two are supposed to be n's. Okay, so you can prove the other way. It's somewhat easier, that if n divides the power k, then k is equal to n to the s. Okay, then we can rewrite a to the k as a to the ns. You can rewrite that using the exponential rules, but a to the n is equal to the identity. Identity to the s is the identity. So if n does divide k, then a to the k is the identity. Right? Another proposition. Suppose I have a cyclic group of order n, and let's take any element of the orbit of A, and we'll call it B. The question is, what is the order of B? We know that B will generate a cyclic group, and we know also that that cyclic group must be a subgroup of the cyclic group generated by A, but we want to know the order of B. Okay? So if B is a power of A, then the order of B turns out to be n over d, where d is the GCD of k and n. Okay? So how do we prove that? Okay. We want to find the smallest integer m such that e is equal to b to the m. All right, that's going to be the order of B. Okay? But we know b is a to the k, so b to the m is a to the km. Okay? All right, so by proposition 98, this is the smallest integer m such that n divides km. Okay, now notice that if n divides km, I can divide both sides of this by the greatest common divisor, because d, the greatest common divisor of n and k, divides n, and it also divides k. Right. So if n divides km, that means n over d divides m times k over d. Okay. Since d is the greatest common divisor of n and k, that means that these two numbers must be relatively prime. And if n over d divides m times k over d, then n must divide m. Then n over d must divide m. And the smallest such m is n over d. So what does that show? We found the smallest integer m such that b to the m is the identity. And it must be n divided by the greatest common divisor of n and k. Okay, that's it.